Good morning everyone. Today I am going to give the lecture on AM modulators. My name is K.Purushotham. I am from EC department, working as assistant professor in MLR Institute of Technology and MLR Institute of Technology, Hyderabad. So today what I am going to cover is what are the different types of AM modulators. So there are two types of AM modulators are there. One is square law modulator, another one is the switching modulator. Okay. So the overview of the course, whatever I am going to cover today is nothing but AM modulator. So what is AM modulator? So still now what we have concentrated, amplitude modulation we have completed, and single tone modulation also we have discussed. So in the amplitude modulation, how to generate the AM wave, and after generating, what is the expression for the AM wave, amplitude modulated wave, that we are representing as a S of t. Next to single tone modulation, we have calculated the bandwidth and we have calculated the power. So today, what are the methods we are using for the generation of the AM? So here AM modulators are circuits used to generate, modulators are the circuits used to generate amplitude modulated signals, where the amplitude of the high frequency carrier is varied according to the message signal. So high frequency carrier amplitude is varying. The high frequency carrier characteristics are changing according to the message signal. So that we are calling it as a amplitude modulation, frequency modulation, phase modulation. In amplitude modulation, amplitude of the carrier is changing according to the modulating signal. So what are the methods we are using for the amplitude modulation generation? So first one is square law modulator, second one is switching modulator. So what is the square law modulator? The square law modulator is the one circuit diagram which contains the non-linear devices like a diodes and a transistor we are using as a square law device, and the output contains carrier frequency, message frequency, sum and different frequencies. Okay, sum of the frequencies FC plus FM and difference frequency FC minus FM, and containing the band pass filter. The output of the square law modulator is connected to the band pass filter, which is allowing the desired frequency component of the modulated signal. Okay, see here the block diagram. If I am concentrating, the square law modulator block diagram is containing M of t is the message signal, which is nothing but the message signal. Message signal. AC cos 2 pi FCT is nothing but the carrier signal. Message signal and the carrier signal. Okay, both we are applying to the summer. Both we are applying to the summer. The summer is adding the two signals. So the added output of the signal we are representing V1 of t. V1 of t is nothing but M of t plus AC cos 2 pi FCT. Modulating signal plus carrier signal. And that is applied to the square law device. That is applied to the square law device. So that is nothing but the square law device is the non-linear device. Okay, non-linear device like a diode. The characteristics of the diode are closely related to the square law characteristics. So the diode what we are using for the square law modulator, which is operated in the non-linear region. So anyhow the diode and transistors are the non-linear devices. The characteristics if you are observing, those are not linear, they are non-linear characteristics. So the diode if I am taking, the cut-in voltage is 0.7 and this is the non-linear characteristic. Okay, the linear characteristics are like this. But diode is not a linear device, it is a non-linear device. So the diode we are using for the square law modulator. Diode we are using as a square law modulator to generate the amplitude modulated wave. So the output of the output of the square law device, if you are observing, it is containing in the form of V2 of t, which is nothing but K1 V1 of t plus K2 V1 square of t plus K3 V1 cube of t, and so on values that are existing. Okay, so the V2 square law modulator characteristics, if you are representing that one, it is containing V2 of t is equal to K1 V1 of t plus K2 V1 square of t, and so on values. Okay, n number of harmonic components are there. So now where K1, K2 are the constants. K1, K2 are constant, and substitute V1 of t in equation number 1. So V1 of t is nothing but, what is the V1 of t? M of t plus AC cos 2 phi FCT. So here K1 V1 of t, V1 of t is nothing but M of t plus AC cos 2 phi FCT plus K2 V1 of t is nothing but M of t plus AC cos 2 phi FCT whole square. Okay. So if you are expanding that one, K1 M of t plus K1 AC cos 2 pi FCT plus K2 M square of t plus K2 AC square cos square 2 pi FCT plus 2 K2 M of t AC cos 2 pi FCT expression we are getting. Okay. So among those all the terms, K1 M of t plus K2 M square of t, I am rearranging this expression, plus K2 AC square cos square 2 pi FCT plus 2 K2 M of t AC cos 2 pi FCT plus K1 AC cos 2 pi FCT. Okay, here the two terms, these two terms I am taking is nothing but here K1 AC cos 2 pi FCT plus 2 K2 M of t AC cos 2 pi FCT. So here what I am taking is K1 AC common, so that can be represented as a 1 plus 2 K2 by K1 M of t cos 2 pi FCT. Okay. So this term, what is the term? K1 AC cos 2 pi FCT to K2 AC K2 M of t AC cos 2 pi FCT. Okay. So if you are taking, this is the similar to the amplitude modulated wave. Okay. What is the amplitude modulated wave? AC cos AC 1 plus Ka M of t cos 2 pi FCT. The amplitude modulated wave is AC cross 1 plus Ka M of t cos 2 pi FCT. So this is the original amplitude modulated wave. The output of the square law modulated is also containing this term. Okay. So what about the other terms? So if you are seeing here, so the last terms of the above equation represent the desired AM wave. Last terms, those are nothing but those terms are K1 AC plus K1 AC of 1 plus 2 K2 by K1 M of t cos 2 pi FCT. Okay. So these are the desired component and remaining terms are unwanted component. So those are the unwanted component means here K1 M of t, only the modulating signal is there, multiplied with the K1 constant, only modulating signal. Directly we cannot transmit the modulating signal. Okay. So that is not possible, as the antenna size required for transmission of the modulating signal is very, very high. And if you are transmitting the modulating signal for the longer distance, the signal strength is going on decaying as you are traveling for the longer distance. Okay. So those are the so many drawbacks are there. We cannot transmit the modulating signal directly. Next term is nothing but K2 M square of t. M square of t is nothing but non-linear term. Okay. So M square of t is the non-linear term. We are not at all transmitting, and square is nothing but high frequency. Frequency is multiplied. Next to AC square cos square 2 pi FCT. Only it is containing the carrier signal. It does not containing any information. So only carrier also we are not able to transmitting. Okay. Only carrier also we are not at all transmitting directly. Okay. So here directly we cannot transmitting the high frequency component. This is cos square theta is nothing but 1 plus cos 2 theta by 2. This can represented as a 1 plus cos 2 theta by 2. 1 plus cos 2 theta by 2 is nothing but high frequency component. So carrier frequency multiplied with 2, that is very, very high frequency. So this high frequency component we are not at all transmitting. So KCM of t not transmitting, and high frequency component we are not transmitting, and this is the nonlinear term we are not transmitting. So only the wanted components are K1 AC cos 2 pi FCT plus 2 K2 M of t AC cos 2 pi FCT. Okay. So this term how can we eliminate? These terms can be eliminated by using the band pass filter, which is connected output of the square law modulator. So here the output of the square law modulator is applied to the band pass filter. So what band pass filter is doing? It is allowing only the band of frequencies. It will allow only band of frequencies from F1 to F2, and remaining frequency it will not allow. We are designing the band pass filter such a way that it will concentrate only the message signal to pass through it, and it will not allow other high frequency signals and low frequency signals below message signals. Okay. So it will allow only the message frequencies which are designed as per our requirement. So now by using the band pass filter, the remaining frequency components are eliminated. So the output of the square law modulator expression is similar to the AM wave. Okay, similar to the AM wave, AC cross 1 plus KM of t cos 2 pi FCT, where Ka is the amplitude sensitivity, where Ka is amplitude sensitivity. This is nothing but amplitude sensitivity. Amplitude sensitivity. In square law modulator, Ka can be represented as a 2K2 by K1. The amplitude sensitivity in the square law modulator we are representing as a 2K2 by K1. And the remaining terms, K1 is the scaling factor. Okay, here the K1 is the scaling factor. So the expression what we derived is the similar to the amplitude modulated wave, only the amplitude sensitivity can be represented in terms of 2K2 by K1. Okay, this is about the square law modulator. The next modulator is switching modulator. So here also the nonlinear device we are using. There the nonlinear characteristics of the diode we are using. Here the diode we are using as a switching element. Okay, how the switching operation can be performed by using the diode, here we can explain about that part. So the following block diagram of the switching modulator, here also the AM modulated wave can be generated by applying the two input signals. One signal is modulating signal, another one is the carrier signal. Okay, the characteristics of the carrier signal we are varying according to the information signal. The information signal I am applying here, and the carrier signal I am applying here. The carrier signal is the high frequency signal. Information is nothing but modulating signal or baseband signal or original signal we are applying here. So these two signals we are applying to the summer. The output of the summer is containing V1 of t, which is containing the M of t plus AC cos 2 pi FCT. Okay, so that is passed through the switching diode. That is passed through the switching diode. So here the diode which is acting as a switch. See here, the difference between the square law modulator and the switching modulator is the square law modulator operated in the non-linear mode, where in the switching modulator the diode has to operate as an ideal switch. The square law modulator diode is operating in the non-linear mode. Here the diode is operating as a switch. So V1 of t is nothing but M of t plus AC cos 2 pi FCT, that is applied to the switching diode. Okay, so now the expression what I am representing is V1 of t is M of t plus C of t. Okay, so next the output of the diode which is acting as a switch. So the diode is acting as a switch. Here the operation of the diode can be implemented if the input signal V1 of t is applied as the input of the diode. V1 of t I am applying as an input to the diode. So assume that the magnitude of the modulating signal is very small when compared to the amplitude of the carrier signal. First, what we are assuming? Amplitude of the modulating signal, that is AM, is less than AC. AM is less than AC. So the diode is on. Now D on. Diode is on. If C of T, diode is on, and AC less than 0, that is nothing but C of T, carrier signal amplitude is less than 0, the diode become off. Diode become off. The operation of the diode can be controlled. We are assuming initially M of T amplitude is less than the carrier amplitude. That is the first condition. And C of T is greater than 0. Here C of T is greater than 0. C of T greater than 0. That is nothing but AC is greater than 0. AC, that is amplitude of the carrier signal, is greater than 0. And amplitude greater than 0 at the same time less than the amplitude of the modulating signal. Next, AC amplitude is less than 0. So in that condition diode is off. So diode, to perform its operation, we are giving the sufficient input signal. If the input signal greater than the cut-in voltage of the diode become on. Diode become on means it is acting in the forward bias condition. If the input signal is less than the 0.7 volts, it is acting in the reverse bias condition. That condition we are calling it as a off state. So diode is on and off. So by performing the on and off operation, the output expression for the diode is nothing but V2 of T. The V2 of T can be represented as V1 of T into X of T, where X of T is nothing but periodic rectangular pulses. Periodic rectangular pulses or periodic pulse train with a time period T is equal to 1 by Fc. Periodic pulse trains with a time period T is equal to 1 by Fc. So how can we represent X of T? X of T. So this is the X of T signal in the diode where it is operating on and off. To the diode we are applying the carrier signal, periodic rectangular signal. Based on the amplitude of the carrier, the diode is on in a particular duration and diode is off in a particular duration. Okay, in this duration diode is on, in this duration diode is off. So the periodic rectangular pulse X of T, what we are representing, can be represented graphically like this. So the Fourier transformation, any periodic signal can be represented by using the Fourier series. So periodic signals we are representing Fourier series, aperiodic signals we are representing by using the Fourier transformation. So here the periodic pulse train can be represented by using the Fourier series as X of T is equal to 1 by 2 plus 2 by 5 summation n is equal to 1 to infinity minus 1 to the power n minus 1 by 2n minus 1 cos of 2 phi 2n minus 1 into FCT. Okay, so finally we are approximated 1 by 2 plus 2 by 5 cos 2 pi FCT minus 2 by 3 pi cos 6 pi FCT plus dash dash dash. The expansion is going on as the n is equal to 1 to infinity. The values, if we are going on substituting the value of n is equal to 1, 2, 3 and so on value, so the expression is infinitely, it is extending. Okay, it is infinite series. So now substitute V1 of T and X of T values in equation number 2. What is the V1 of T? V1 of T is nothing but M of T plus AC cos 2 pi FCT. Okay. So V2 of T is nothing but V1 of T multiplied with the X of T. Okay. So already we know V2 of T is nothing but V2 of T is equal to V1 of T into X of T. V1 of T into X of T. So X of T is the, this is the expression. V1 of T is nothing but M of T plus AC cos 2 pi FCT. So V1 of T is nothing but M of T plus AC cos 2 pi FCT. Okay, AC cos 2 pi FCT. That is multiplied with the X of T. Okay, final what is the expression we are getting? So M of T multiplied with 1 by 2. M of T by 2. M of T multiplied with 2 by 5 cos 2 pi FCT. So that is nothing but, what is the value we are getting? M of T by 1 by 2. Then AC by 2 cos 2 pi FCT. First M of T we are multiplying 1 by 2. Then AC cos 2 pi FCT also we are multiplying with 1 by 2. So m of t by 2 AC cos 2 pi FCT by 2. Okay, next m of t we are multiplying with 2 by 5 cos 2 pi FCT, that becomes 2 m of t by 5 cos 2 pi FCT plus AC 2 AC by 5 2 AC by 5 cos into cos square 2 pi FCT and so and value as we are multiplying these terms with these terms. So we are getting the expression like this. Okay. So the approximated expression what we want to obtain is AC by 2 1 plus 4 by 5 AC into m of t cos 2 pi FCT plus m of t by 2 plus 2 AC by 5 cos square 2 pi FCT minus 2 m of t by 3 pi cos 6 pi FCT minus 2 AC by 3 pi cos 2 pi FCT cos 6 pi FCT plus and so values we are getting. Okay. So among the n number of terms, we are taking the above expression represent the first term in the above expression is representing the desired AM wave. So what is the first term? AC. The first term is nothing but this one, AC by 2 1 plus 4 by 5 AC m of t cos 2 pi FCT. Okay. So this is the desired signal. So that is the wanted signal or desired signal. And the remaining terms are the unwanted terms. The remaining all terms, this is the wanted and these all terms are unwanted. These unwanted terms can be eliminated by using the band pass filter. So the only it is allowing the desired signal. We are designing the band pass filter such a way that it will allow only the message signal to pass through it and it will not allow the other high frequency component. So with the help of the band pass filter, we can pass only AM wave and eliminate the remaining terms. Only we can pass the amplitude modulated wave and the remaining terms can be eliminated. So here it is also similar to the original amplitude modulated wave AC cross 1 plus Ka m of t cos 2 pi FCT. Okay, here instead of AC, AC by 2, that is nothing but the scaling factor by 2 and amplitude sensitivity Ka in the Ka can be represented as a 4 by 5 AC. 4 by 5 AC. So the scaling factor is 0.5 and the amplitude sensitivity is 4 by 5 AC. So here what we have discussed today, first what are the different types of modulators we are using for the amplitude modulation. So first modulator is square law modulator. So there we are using the diode is the square law element and output of the diode is connected to the band pass filter. So there the diode we are using in the nonlinear region and we are obtaining the square law modulator output as the amplitude modulated wave and that is passed through the band pass filter. It is allowing only the amplitude modulated wanted signal and unwanted signals can be eliminated. And the next modulator is nothing but switching modulator. Here also the diode we are using as a switching element. There diode we are using as a nonlinear element. The expression of the diode output expression is different. Here the diode output expression is the different. So here diode we are using as a switching element. Here the carrier signal and modulating signal both we are applying to the input of the diode. In the diode there one more signal we are applying, the periodic rectangular pulses we are applying. Based on the periodic rectangular pulses C of t, the diode is switching on and off. So based on that one, the output waveform is generated. The output waveform whatever is generated is passed through the band pass filter. Here also the wanted terms we are allowing and unwanted terms we are removing. Okay. So this is about the today lecture. Thank you.